and good morning, everyone. We have a large population of people online, and so I hope you can hear and see us well, and welcome to the meeting. I'm going to give a high-level overview of a couple of things here in this presentation, if I can find my clicker. Number one, I'm going to talk about the EQSIM simulation framework. Most of the work that you're going to see is a direct derivative of an application of a special new fault-to-structure earthquake simulation capability that was built for the DOE called EQSIM for earthquake simulation. I'm going to touch on that briefly. I know a number of you have seen that and heard about that before, but just for consistency, I'm going to go through a very quick highlight about EQSIM and the unique attributes of EQSIM and why it's important, the computational achievements that have been made, why that's important to generating a very large simulated ground motion database. That's number one. Number two, I'm going to talk about the plan for the open access data sharing, and I'm going to talk about, at a high level, what is currently in that database. This is, Holland had mentioned there's been 3 workshops now between PEER and LBNL. Arguably, this is the most consequential one because we're actually going to be rolling out this product and making it open access essentially in a phased way after this workshop. So this is a very, very important time, and it actually represents the culmination going all the way back to the start of the development of EQSIM of about 6 or 7 years of work. So it's a really, really important milestone for us. There have been 2 major DOE Department of Energy projects that have funded this work that I wanted to acknowledge. The first provided us with our computational tools, and that's the Exascale Computing Project. It ran from 2017 to 2023. The fundamental purpose of that project was to develop the next generation of supercomputers, scientific-based supercomputers for the United States. And some of you may know these were GPU accelerated platforms, and the objective was to develop the first exaflop computer, which has since been achieved. So I'm going to touch on that a little bit. That was really the enabler in the support for us to develop the EQSIM tools. Number 2, now that the ECP project has completed, we're really transitioning from a computational R&D focus to an application focus. And that has been picked up by the DOE Office of Cybersecurity, Energy Security, and Emergency Response. The U.S. Department of Energy has a lot of stakeholders in the energy domain. That's why they're called the Department of Energy. And that particular office is responsible for things like cybersecurity of our energy systems, all the way to natural hazards and the effects of natural hazards on our energy systems. So they are actually supporting this work now, and that's really providing the mission pull, if you will, as we go forward in the rationale for the things we're doing. And they are, in fact, the ones that are supporting the development of this simulated ground motion database. So let me speak first to the Exascale Computing Project. And as you see on the left-hand side, developing the world's fastest advanced supercomputers coming out of the US, the next generation of supercomputers was the objective there. The idea was to exploit these new types of chips, GPU accelerated chips, which are different than CPU chips. They can process information in parallel on the chip instead of serially, and take advantage of that technology to build the next generation of supercomputers. That was a success story. Frontier is the world's first exaflop computer with 9,400 nodes, and it resides at Oak Ridge National Laboratory. So the focus of that project through that first part was to get that computer designed and built and online, and they were successful doing that. Just to add, if you think about what an exaflop computer is, this is the number of floating point operations per second that computer can execute. A billion floating point operations per second. So it's an extremely powerful and extremely large computer. Because of the new changes in the architecture of these machines, DOE decided to support a set of key applications to run on these machines in parallel to the development of these machines. The normal duty cycle for these types of machines is to develop the machine and then let the software spend 2 or 3 years catching up. The DOE, I think, correctly realized that that was not the optimal model in this case because the architectures were so new. So they had a competitive call for proposals. People submitted various science and engineering applications that really demanded this level of supercomputing, and 24 were selected. The EQSIM that you see on the lower right was one of those that was selected. And the proposal for EQSIM was to model earthquake processes all the way starting from the fault rupture the propagation of seismic waves through the Earth, the very heterogeneous Earth, and then the detailed interaction of those seismic waves with infrastructure to answer a number of questions. Specifically, what does the regional distribution of ground motions look like? As Holland showed, the data, particularly in the near field, is extremely sparse, so there's a lot to be learned by utilizing simulations in virtual space to understand the distribution and amplitude of these ground motions. Secondly, and not so much the topic for today, but the topic for the future, is how do these seismic waves actually interact with infrastructure when they get to that site? We've long idealized site response in the engineering community as a one-dimensional site response calculation for idealized vertically propagating waves. These types of tools can allow us to go back now and critically evaluate some of those things and see if all those things that we've assumed for the last 3 decades are actually applicable, and we're seeing some of those are not. So ECP was really the motivation for the development of our software. So what do we do under ECP? Well, we started with the SW4 code, which is a 4th order in space and time finite difference code that was originally developed at Lawrence Livermore National Laboratory as our baseline code. And the core of the compute engine for EQSIM is in fact our geophysics simulations of the ground motion. So we started with SW4, but we made a whole slew of advancements in SW4, as you can see on the right-hand side. And the reason we did this, we had to get ready for these GPU accelerated machines, but we really wanted to push the cutting edge limits of simulation with this tool. So we did things like, going down the list, developed advanced mesh gridding that was most efficient for the natural gradation of the Earth. We got readiness for GPU. We had to recode all the CPU-based coding, and so we had to decompose computational loops and subtasks and get those ready and optimized on GPUs. We had to deal with massive data management. And a recurring theme you're going to hear through the day today, and hear more on this later, is you really have to have a schema in place for efficiently handling these huge data sets. I've been to multiple meetings of different organizations talking about simulated ground motion data sets, and I haven't heard a scheme emerge yet for handling the very, very large data, particularly as we want to scale up to higher frequencies and higher resolution. So that was a very big focus of this. And then finally, we did enhancements to some of the physics, like the Graves-Pitarka rupture model you're going to hear about a little later. So where did we get to as a result of this work? For DOE, we had to have a canonical test problem. They just didn't give us 7 years of funding and say, go do good things. We had to have metrics that were defined for us for each project. And we had something called the figure of merit that we had to try to achieve as a result of all these developments. For us, we built a large regional model of the San Francisco Bay Area. And throughout the life of the project, we continually computed earthquake simulations in that domain to demonstrate our performance to DOE and our increase in performance. So where did we start and where do we get to? This is the frequency resolution that we had in that model. When we started, it was about just under 4 hertz on the Cori CPU developed system at Lawrence Berkeley National Laboratory. As time went on, and as our algorithms or enhanced algorithms were improved, like mesh refinement, and the machines got bigger and faster with the first GPU accelerated system here, Summit, and then the exascale system, you could see we went from 3 hertz, just under 4 hertz, to 15 hertz. That's a lot. It can be shown in this computational domain that the computational effort varies as the frequency to the 4th power. And so you can see that this was a big step up in terms of frequency resolution. We also wanted, in parallel, to look at developing the ability to do a resolution of near-surface soft sediments. Often in these calculations, a high cutoff in the computational models is established because it's very, very difficult to represent those soft sediments with very short wavelengths in the computational model. So in parallel, we started out with a cutoff in this Bay Area model of 500 meters per second, and then gradually hammered that down to about 140 meters per second. So this is where we started, and this is where we ended, which was a big jump in computational effort. So we reached the resolution goals that we wanted to achieve for that project. Then we had to worry about the speed. It doesn't do us any good if we have to do a heroic calculation of an earthquake and it takes us, 3 months to do that, even if we can get that done in that time frame. We need to be able to explore the parameter space, for example, for a simulated ground motion database, and vary the parameters in the model because there's uncertainty in those parameters. We don't know how the fault's going to rupture. prior to the earthquake. So we have to vary that. So in addition, we needed speed. So I'm showing you here for a 10 hertz simulation of the San Francisco Bay Area, I'm showing the wall clock time on Frontier as we increase the parallelism in the number of compute nodes. And you can see that for that 10 hertz solution in the Bay Area with 221 billion grid points in this domain, we could, if we go to a full Frontier machine, we can run that now in 6 hours. And so that opens the aperture of being able to do a large number of realizations. So you can see here in this table, if we're running a 5 hertz solution with a VSIM S-MANA 250, we can do that in 1.8 hours now on Frontier, which is really enabling because you can run all kinds of parametric studies. For a 10 hertz solution, we can run that in about 6.3 hours. And for a 15 hertz solution with a VSIM S-MAN of 140 meters per second, we can now run that in about 29 hours. So to finish up this discussion of the software technology, the takeaway message is now we can really, with these capabilities, begin to explore the parameter space and the variabilities that influence ground motions in a very constructive way. What I'm showing you here are 5 of our realizations that we actually computed for the database. Each one of these is at a different hypocenter. You can see here, looking at this, that there's great directivity for these 2 different rupture scenarios at the rupture hypocenter to the north or the south. And I can assure you the ground motions look very, very different for those 2 particular rupture scenarios. So we really need to be able to run a large number of these, and the takeaway message from that discussion of the software is that now we can. So I'm going to transition quickly into the notion of the database. And back in 2021, at the height of the pandemic, we had a joint workshop with Peer, and it was really well attended. There were about 261 international participants, and we began to poll people, experts in the field, both seismologists, geophysicists, and engineers. How can we take the best advantage of the ability to simulate these types of ground motions now? And we had a poll, much like we're going to have today, and this is what came out of that poll. The number one response was availability of a database of synthetic ground motions with open access that people can get their hands on in an efficient way. And so that was really, back in 2021, we really started thinking and planning towards a simulated ground motion database based on this feedback. And that makes sense. There's very few people that have that large of a computer and can run this scale of problems. And so being able to provide this open access data is important. And that's exactly where we're going in the topic of today. There's also a notion to, assess those ground motions and develop some sort of acceptance or check of those motions, and we've been working on that. I'll mention that briefly. And then finally, an effective and operationally efficient user interface. Some of the people that had used the NGA database said, don't mess up my ability to pull data in that format from my database and utilize that. So it was important to have that feature as well. So our initial database that we're going to be talking about a little bit today and going forward is really based on the San Francisco Bay Area. We already had this model built, so we're leveraging that. We decided to limit some of our parameters initially for this database. We're running to 5 hertz to keep the data set manageable. 29 billion grid points, because we can run that fast. We're currently using a fully linear viscoelastic model. In the future, we can potentially do some nonlinear analysis near surface, and so you can see the attributes of this model that we based this on here. There's 2 activities ongoing. One is being done by the national laboratories, primarily, with some help from some of the universities. And so activity number 1 is the completion of the San Francisco Bay Area regional simulations. We've been at this almost a year now in terms of tuning up our velocity model and getting everything ready and checking our velocity model and running these realizations. And so we now have 50 of those realizations in hand. This is really a multidisciplinary problem, so we've got engineering, seismology, computer science, and a couple of universities like Floriana Petrona at University of Nevada and ET at UCLA, who's doing some simulations in the LA Basin, are working with us as well. And we've got a really, really great group of postdocs and PhD students, and I would strongly encourage you to look at their posters to see what each of those are individually doing in this project during the break outside. Activity number 2, and Holland is going to speak to this in some detail, is the development of a user interface. It's going to draw from Peer's experience working with the engineering community, interfacing with the engineering community from the NGA database, and they have already developed this database. It's been operational and working for a few months now. So our workflow looks something like this that we've developed just for this database. We run the regional scale simulations on the Big Iron at the national laboratories. Some of those we run at Oak Ridge, some of them we run at Lawrence Berkeley National Laboratory. We could have the options, and this is where the data is, I can't emphasize this enough, being able to efficiently manipulate and store this data is absolutely crucial. So we've implemented a number of options there. We can compress the data with lossy compression. We can uncompress the data. We can downsize in space. We can downsize in time. All those options are at our disposal. So we deliver fundamentally from our simulations ground velocities to peer. Peer integrates and differentiates those to get the ground acceleration and displacements, and then those are placed on the peer server for access, and you'll see that interface. So for the first 50 realizations, we really have focused, as I kind of hinted in that animation, on the sensitivity to the fault rupture. Everything starts with the mechanics of the fault rupture and how that energy is released. And so we're pleased that we have Arvind Patarka on our team, and he has been developing the rupture models. We've got, for this first database, 25 pure stochastic rupture models, and also 25 stochastic plus deterministic patch rupture models that he has put together for us. The simulated ground motions for the 50 motions is on the peer server. We've looked at hypocenters, moving the hypocenters around for these ruptures to 5 different hypocenters. That 50 ruptures at 2 kilometer spacing results for all 50 to a little over 1 million time series on the peer server at 5 hertz, and so that's already a pretty good sized data set. It's much bigger than the NGA data set. It's about 700 gigabytes with pure ASCII files, which is the format that Peer likes to share with people. So those are all there and ready to go. We're backing that up, however, with very, very high fidelity motions that we're storing on the supercomputers at Lawrence Berkeley National Laboratory. For a 5 hertz solution, the actual grid spacing near the surface is 6.25 meters for a 250 meter per second cutoff. So we have 110 billion time series that we have to compress and time downsample, and we store those as backup on the server because we eventually want to utilize those motions and create a 3D velocity or a set of motions near the surface so we can do engineering things like apply DRM and so forth. We check things. We've gone through a fairly extensive study. We've tested our EQSIM simulations in the Bay Area by looking at small events. There's a paper out, Camilo Pinillo-Ramos, who is a PhD student and then postdoc here at the time, has actually done that work. And Floriana and Ree Nakata have been looking at comparisons with ground motion prediction equations and so forth to check reality. So we've done quite a bit there. There's a lot to understand and look at in these motions as you start to browse these. I'm just showing you a couple of examples of engineering response spectra. You can see all 50 realizations in grayscale. So you can immediately with your eye see some of the within event variability, and then you can see going across to different sites, you can see some site response in some of these other stations. So there's just a tremendous amount of data to go through and understand. Since January 2025, we have commissioned and worked with a set of 15 beta users of this data set. We wanted to have these folks take a look, utilize some of these motions, and kick the tires before we open it up to the broad community. And you can see here, as you look across, we have a very broad swath of people from researchers to engineering practitioners to federal agencies to state agencies and so forth. And that's been a useful exercise. And so I guess I would just note that this group has downloaded over 5 million time series and looked at those time series since January. We don't see just generating the surface motions as the end game as we think about engineering applications. And we'd eventually like to get to the point where we save a near surface volume of motion so people can apply the domain reduction method and understand how these seismic waves interact with their particular structures and foundations and potentially look at nonlinear behavior and site response. And so a couple of our beta users, Pedro Arduino, who couldn't be here today, he's on travel, and Frank McKenna have actually been looking at taking our motions from that database in a very efficient way and applying the domain reduction boundary motions to the subdomain so they can do this type of detailed analysis within the engineering calculations, utilizing those 3-dimensional motions in a near surface veneer. So I'm running over time. I'm going to stop there. I've got 10 seconds left. I'll just say that I'll second that the community input for defining additional capabilities enhancement is absolutely crucial. We've already gotten some feedback on this from paper reviewers as well as from community folks saying this is really important, you ought to have this, you ought to have this intensity measure. So we can't do everything, so we need to prioritize those in a constructive way. And so we really want the feedback from the community, and you're going to get a questionnaire today. I would also note that if you jump on, you want more very detailed information, you can jump on the website when you get access, and there are links to open access papers that have a much more detailed evaluation and discussion of some of these things. So with that, I am out of time.